Hello, welcome to Lecture 2B. We're going to be discussing nuclear chemistry out of Chapter 19. I'm going to start with some definitions. We've got radioactive, which is the spontaneous decomposition of a nucleus to form different nucleus or different nuclei. We've got alpha particles, which we use the Greek letter alpha, which is a helium nucleus produced in radioactive decay. We also have beta particles, which use the Greek letter beta, and that is an electron produced in radioactive decay. And then we have a gamma ray, which uses the Greek letter gamma, which is a high energy photon produced in radioactive decay. So we've got some nuclear equations that we're going to look at. First one, we've got radium-222 that produces an alpha particle. So we start off by taking the symbol for radium, we put the atomic mass over the atomic number, and we're told it produces an alpha particle, which we use helium for. The mass of helium is 4, atomic number is 2. And then if we were to take 222 minus 4 and 88 minus 2, we get a result of a mass 218, atomic number 86. We reference the periodic table, find out that 86 is radon. Our next example is iodine-131 produces a beta particle. So I write down iodine with its mass over atomic number and its symbol. Told that it produces a beta particle, which an electron has no mass, and it doesn't really have an atomic number either, but it in effect is -1. So the difference then between 53 and -1, or what plus -1 gives me 53, will be 54. If I look at 54 on the periodic table, I find that it's xenon, and then I rewrite the mass because it's affected by 0. And then with gamma radiation, it doesn't affect our particles, our radioactive isotopes. We can also date by radioactivity. So half-life is the time required for the number of nucleides in a radioactive sample to reach half of the original number of nucleides. So if I was to use carbon-14 dating, which is a method for dating ancient wood or cloth on the basis of radioactive decay of carbon-14. So the half-life of carbon-14, I'm told, is 5,730 years. If a sample is found and dated and 25% of the carbon-14 is found to be remaining, how old is the sample? So I'm going to start off saying, okay, I originally started with 100% of carbon-14. So I'm going to put that in a box, and these boxes are where I'm going to keep track of how much of a sample I have, and I'm going to divide those with an arrow. And this arrow is going to represent a half-life. So this is one half-life. After one half-life, I have 50% of the original material. So now I have 50% of my sample remaining. And then it's going to go through another half-life. And now I have 25% of my sample remaining, which is what I want to get to. And then I can say, okay, one half-life is 5,730 years. So how long has it been after two half-lives? So how old is the sample? So take 5,730 times 2, you get 11,460 years old. We've got two definitions to end up our lecture today. We've got fusion, which is a process of combining two light nuclei to form a heavier, more stable nucleus. So fusion is a putting together process. Fission, process of using a neutron to split a heavier nucleus into two nuclei with smaller mass numbers. So fusion is building up, fission is breaking down. So that ends our lecture on nuclear chemistry.